conference, a great topic. I'm Glenn Rudebusch from the San Francisco Fed. I'm privileged to chair the second half of this session on climate change and the economy. Here we turn to the physical impacts and risks of climate change, which, as Sarah Breeden noted earlier, these are already materializing. One of the most important characteristics of these risks is their heterogeneity. Climate-induced changes in, for example, the global water cycle are leading to more flooding in some areas, but more droughts in others. So getting this granularity and this high resolution is crucial. And our first speaker is a pioneer in quantifying these granular costs of climate change. Solomon Hsiang directs the Global Policy Laboratory at the University of California at Berkeley. He co-founded the Climate Impact Lab, which is modeling the costs of climate change sector by sector and community by community around the world. Today, Solomon will talk about the global impacts of climate change. Thanks for joining us.
Thanks, Glenn, for that introduction. I'm going to share my screen. Great. So thank you very much for having me. My name's Solomon Hsiang, and like I said, like Glenn said, some of the work I'm going to show you is from my team at Berkeley, and some is from the Climate Impact Lab, which is a consortium of researchers from around the country. I think when we talk about the physical impacts of climate change, it's very important to recognize that what we expect to see in the future is a very different world than we inhabit today. So in this picture, what we are doing is we're showing the summertime temperatures of countries around the world organized on the horizontal axis in a high emission scenario and in a cool scenario. And what you see is that in the future, a country like Germany is expected to have summertime temperatures that are similar to Spain. Other countries like Uganda would be expected to have summertime temperatures similar to Saudi Arabia. And countries like Sudan and Mali will be experiencing temperatures that have not been seen anywhere on the planet historically. So it's a completely different world. Now, at the same time, how we get to that world is a very gradual process. So what I'm showing you here are model projections of climate change over the coming century. And what we see is about a 1 degree C change over 30 years, which, if you break it down, means that every single day over the next several decades, we're going to be experiencing climate change, but it's very small. It's going to be about 1 in 10,000 degree, well, 1/10,000th of a degree per day. And so climate change should be thought of as a very long sequence of very, very small daily changes. And so in the research where we try to understand what are the physical impacts, we essentially are trying to understand and distinguish between different hypotheses about whether or not the climate has a small impact or a large impact on society or different sectors. And it's been historically a very difficult problem to answer because the climate itself is very high dimensional, society is very high dimensional, and there's many confounding factors. Luckily, there's been a lot of progress in the last several decades. And so you can think of the ideal experiment one would like to do. You take two planets, you change the climate of one, you don't change the other, and then you compare the macroeconomic performance of the two societies. That's a difficult experiment to implement. What we actually can do is something that approximates that experiment. And what we study is how we reconstruct the historical exposure of different populations to different physical conditions. And then we observe that as those conditions change over time, how does the economy or elements of the economy respond? So you can think of a high climate exposure period as like the treatment, a low climate exposure period as if it were the control. So a simple picture that depicts kind of what we're doing in this whole vein of research. If you look up here at the very top panel, panel A, you have two probability distributions that describe different distributions of outcomes, called it climate 1 and climate 2. And over time, what we observe in actual data are sequential draws from this distribution. So here, time is actually going downward. And what you see are a sequence of events drawn from climate 1. And what we observe in the outcome data is a sequence of outcomes, so down here on panel D, that are revealed over time. And what we try to do in this type of work is we use econometric techniques to recover the curve we see here in panel C, what's labeled as a dose response function, that describes how these climatic variables map onto different social outcomes of interest. And then what we can do, and when we think about the future, is we can reconstruct what climate 2 might look like. We can map it through these functions And then that gives us a final distribution that has changed, shown here in panel E, and that allows us to quantify what the economic and social risks might be. Now, of course, you also see that this function here has changed as the climate has changed, and that might be because populations adapt. And so that is one of the frontier questions in this line of research, is to ask, how is it that populations will be adapting down the road? Now, in this vein of literature, there's essentially two styles of work. We've been participating in both of them, and I'll show you brief examples of both. There's the top-down approach, where you essentially look at large aggregates of the economy, things like GDP measures, and you try to understand how they're responding to changes in the climate. Now, that approach has benefits in that it has a very holistic view of the market impacts, and so you really capture many, many things kind of in one fell swoop. In that sense, it's relatively easy, and it's also easier because all the ways in which populations adapt are essentially contained in these metrics, and so it's accounted for implicitly. A challenge of the top-down approach is that it doesn't capture non-market impacts. So anything that's not described by GDP is going to be missed. And in many cases, while we can see what the overall effects are, we don't necessarily understand what's happening under the hood. And that can make things, difficult for policymakers who are trying to intervene. The alternative approach is a bottom-up approach, where we study different sectors of the economy and we try to enumerate those impacts sector by sector and then kind of add them all up to understand what the overall impact is on society. A benefit there is that we can study a non-market impact and incorporate it into those calculations, so something like biodiversity or human health. It also provides a level of detail and granularity that it can often guide adaptation decision-making, and it's also transparent, which is useful, for example, in legal contexts. But a challenge is that you're adding things up one by one, and so of course you're going to miss things, and also it's extremely costly and difficult to do that. One reason is that you have to model adaptation explicitly, the way I showed on the previous figure. So, and before proceeding, I just want to address one point that I get a question very often, which is, how is it that in this top-down approach you are accounting for adaptation implicitly? You said this is very easy. And so for this kind of group of economists, here's a figure from a paper actually with Tatyana, where if you have an Edgeworth box and you're thinking about how the macroeconomy is responding to climate change, if you have some initial equilibrium before the climate changes, and then the climate changes and populations adapt, they reallocate resources, maybe you take the metal that you would have turned into a computer and you instead turn it into an air conditioner, whatever the economy is doing to reallocate products and goods and services, that essentially is adaptation, and the costs and benefits of all those adaptations are going to be captured through the market. And so it is actually sufficient to observe both the costs and benefits of adaptation by observing how total revenue in the economy is changing, shown here by just the single summary statistic, just output. And so that actually makes recovering adaptation effects in the top-down approach substantially easier than in the bottom-up approach. So just to share with you a couple examples so you have a sense of what we're seeing in the literature and understanding around the world. A simple example is to start with tropical cyclones, also known as hurricanes, around the world, trying to understand their impacts. So in a sequence of studies, what we've done is we've actually reconstructed physical models of these storms. So here's the wind intensity inside sort of a characteristic tropical cyclone. And then we take historical data and track how cyclones have moved around the world and over time. So this is a reconstruction of Super Typhoon Joan in the Philippines, and you can see it passing over the northern islands. The color is indicating the intensity of the winds that populations were exposed to. We then go into the historical record, try to reconstruct all the tropical cyclones that have been seen around the world in each different year. In general, there's roughly about 100 per year on this planet. And then we can reconstruct all the cyclones for many different years to get a new data set of exposure for every single country to every single storm that's been observed in the historical record. Linking that data up to GDP data, we can then test different hypotheses about how economic growth might be responding to these large-scale climatic disasters. And so here I've drawn for you, 4 different hypothetical trajectories of GDP growth as they follow disaster. And they all essentially are making different assumptions about how an economy might respond after disaster strikes. Is it the case that an economy grows very fast? Maybe it's stimulated by the disaster. is it the case that the economy slows down relative to its historical baseline, but then later accelerates and exceeds performance that it has observed in the past? Does the economy slow down and then speed up and just sort of recover to its historical trend? Or do we observe that economies slow down and then they go back to growing at their initial rate, but without a period of very fast pedaling, they never catch up to their historical trajectory? When we link together the data sets between the exposure and GDP historically, what we observe is something that looks like this no recovery hypothesis. So you have a tropical cyclone strike sort of an average country, and you observe slightly slowed growth relative to the baseline trend for roughly 15 years with no clear evidence of recovery out to 2 decades. Now, the implications of this, if you look at the magnitudes, are that these events, which are happening 100 times around the world each year, have substantial impacts that are of macroeconomic importance, similar in magnitude to many types of events that we pay a great deal of attention to as a society. And so I think this warrants thinking about these types of events with a level of seriousness that we focus on these other macroeconomic events like currency crises that we generally pay a lot of attention to. Just to get a sense of scale, recently we did some calculations for Hurricane Maria, which was an unprecedented event in the US territory of Puerto Rico. The average location in Puerto Rico was exposed to winds of 125 miles per hour. So just imagine driving your car twice the speed limit and then hopping up on the hood of it to get a sense of what the exposure was like across the entire territory. And when you think about what the overall long-term impacts on the Puerto Rican economy would be expected to be, given what we've seen historically, it will be setting back Puerto Rico several decades of growth in just a matter of a few hours. So these are really dramatic events. If you think about what the overall long-term trajectory of different countries are in different types of climate scenarios, in our analysis, we estimate it's roughly a net present value of about $10 trillion to avoid the intensification of hurricanes around the world. In other work, what we've done is we've studied other types of impacts. So here I'm going to focus for a moment on temperature, which is also going to change as a result of climate change, and ask how it affects growth, sort of using a similar approach. One reason you might focus on temperature and growth is that many other studies of the sub-elements of the economy, so things like capital or labor, are observed to change in response to temperature. So here are 2 graphs from colleagues of mine demonstrating how different sub-elements of the economy respond to changes in temperature. So corn yields increase in productivity slightly up to a critical temperature, about 30 C, and then plummet quite dramatically. Similar, what we see is that daily workers increase their labor supply up to around the same cutoff point, and then that declines as well. And so what you can do is you can sort of set up a simple model of any kind of economy where you have these different factors, they respond to temperature, and then you can ask what would happen to the sum of all their outputs, which is something like total revenue in the economy. And the prediction from that type of model, I won't explain this whole figure here, but you could have different types of inputs. And then when you aggregate over lots and lots of physical space and many different moments in time, the prediction is actually that you should have a function that is smooth and concave and not as sharp as what you see on the ground when observing actual individuals or crops. And when we take this to the GDP data, we actually see exactly that kind of shape. And so this is from a published study looking at how growth rates change in response to changes in temperature. And this pattern we see over and over, where if you're initially cold and you increase your temperature, we observe growth rates within a country to accelerate up to a point. That's where the sort of peak is around 13 degrees Celsius. At around 13, changing the temperature one way or the other has very minimal effect. And then at higher temperatures, we observe that increases in temperature lead to sort of steady declines in growth rates to the tune of about 1% per 1 degree. And that number is important because we see the slope on the right-hand side of this curve here to be one of the most sort of replicable findings in this large literature. Also, just to get a sense of how this curve is constructed, I think people see this and they see the US is at the peak and they think, oh, well, we're just looking at omitted variables bias. But but it's important to point out that this curve is derived by following different countries over time and looking at how they respond to changes. And so it's actually constructed using within variation. So you look at a country like Iceland, these are the actual data points used to construct the curve. Higher temperatures lead to higher growth rates in Iceland year over the last several decades. You look at a country like the United States, looking at annual temperatures, you don't see a very large effect if there's any variation, in part because it's near this peak. I'll show you something different in a moment. And then at these very hot countries, we see that higher temperatures just lead to slower growth rates, and that's visible with your eyes. Now, part of a previous analysis was showing that this actually shows up in wealthy countries as well as poor countries globally. When you look at macroeconomic data here on the left, in work with Tatyana, what we've done is we've looked at counties throughout the United States using a slightly different modeling framework, but the overall approach is the same. And we recover a response, a change in overall economic output of US counties that is very, very similar, with a very similar peak, a similar structure, and a similar decline of about 1% per degree above 13 degrees Celsius. So we think this is fairly strong evidence that this type of relationship continues to persist in some of the wealthiest countries around the world today. Interestingly, you can actually look in the United States over time and ask whether this has changed. What we observe is, in fact, it hasn't changed very much. And strikingly, this slope on the right-hand side of the curve, where you increase temperatures and you decline 1% per degree, has not changed even in the 21st century. Now, since we've released these studies, other people have gone and collected data from other countries and repeated the analysis. And I can tell you it's strikingly replicable using different data sets from different contexts. So many different authors are doing this. I get a notification on Google Scholar like every other week that there's a new paper on this topic. So we call this the marginal product of climate. It's basically asking how the production possibility frontier evolves as the climate changes. And what you can do is you can take this curve and simulate what things might look like going forward. And when you do that using the macroeconomic data, you get a map that looks like this for what GDP impact relative to a counterfactual with no climate change would look like in the year 2100. And so there's a few features to point out. First of all, the northern countries where things are already fairly cool, they can actually benefit or be relatively unaffected by changes in temperature because they're at this point in that curve where things are increasing or relatively flat. But there's a large swath of the global economy where populations are very heavily exposed to high temperatures already. So additional warming leads to sort of disastrous outcomes. If you add those numbers up for the entire planet, the projection for world income would have a central estimate that is about 23% lower than historical baseline. But importantly, there's a lot of uncertainty. And so I think thinking about uncertainty and the uncertainty that climate change injects into the global economy is also an important factor to consider and to actually price when we're thinking about willingness to pay to avoid climate change. The other concern is the fact that many of the places in the world that are most heavily impacted, the hot places in the world today, also tend to be the poorest places in the world. And so we see a very strong divergence in national incomes when you look at different countries ranked by income. Lastly, I want to share with you some of the bottom-up results that we have recovered from the Climate Impact Lab. So this is now switching gears and looking at the completely different approach where you look at the economy and you add things up sector by sector. So I'm just showing you some work that we've done together, sort of as a team, where we are trying to actually do econometric analyses of each one of these sectors shown on the screen. So we're looking at health and agriculture, and even within agriculture, we're looking at all different crops, energy, labor supply, coastal impacts. And I can tell you this is a much harder approach from experience, but it is helpful and it provides valuable insight for other reasons. So one reason this is a hard approach is you actually have to, instead of going out and just getting macroeconomic data that's collected by someone else, you have to go and collect data from all different places in the world who have all different collection systems. So looking at health data or agriculture data from around the world. What we then do is we apply a very similar technique to what I've just shown you, analyzing how changes in the climate might be affecting agriculture or labor supply or energy demand, for example. Without showing you the details of each one of those studies, what I can show you are some projections. And so These are estimated impacts in a high emission scenario from around the world across 6 different sectors that we're studying. And what you see are a level of granularity and detail that is very useful for other types of decision making. So, for example, if you wanted to develop an adaptation strategy to think about human health, you would want to understand where to allocate resources, the same for sea level rise. In many cases, an additional thing you observe is the spatial pattern is quite similar to the GDP result I showed you, where we observe places around the world that are already hot today are expected to experience much heavier impacts of climate change. Not in all cases. So, for example, other fuels is, for example, combustion of heating fuel, which is going to be, consumption is going to decline as things get warmer. And so there's benefits kind of spread evenly around the world. So providing this level of detail is helpful for actual decision making, being responsive to climate change. And then also for policy guidance, what we can do is we can take all those different simulations, add up the impacts we see around the world, and put a dot down for each different simulation run. And what these curves are they're looking at impacts in each category as a function of global mean temperature. So, we often talk about limiting warming to maybe 2 degrees or 1.5 degrees. We are exploring the potential economic impact as we go from 0 to much higher temperatures. And this allows you to think through what the global social cost of these warming scenarios are and how one might use this information to price carbon. So just to wrap up, the research field is moving quite quickly. Climate change, can be understood to be changing the planet through a very large number of very small changes, and we are very good at measuring the impact of those changes on the economy using modern econometric techniques. Those are applied through 2 different methods. The top-down approach is focused a lot on economic growth, and what we see is that the impacts are expected to be very substantial and highly nonlinear. Those measures actually capture the adaptive response of the economy itself as it's trying to cope with changes in the environment. The alternative approach, the bottom-up approach, is very intensive and costly, but it provides very valuable clarity and traceability for mechanisms which are useful for different types of policy intervention. And so at this stage, I just want to emphasize this very last point. When you are making decisions about climate change and the economics of climate change, we now have an evidence base that can and should be used in designing those policies. There are many people who have very strong beliefs one way or the other about what climate change might be worth, but we don't necessarily need to be led by beliefs any longer. We can actually turn to the data. Thank you very much.
Thank you, Professor Hsiang, for that comprehensive discussion. We're going to hold questions and discussion until the end. However, the audience can already start formulating and submitting their questions in the Q&A panel, and we'll get to all of those at the end. Before that, our second speaker on physical risk is Tatyana Deryugina. She's an associate professor in the Department of Finance at the University of Illinois at Urbana-Champaign. Her research interests lie in environmental, public, and behavioral economics. Today, Tatyana will talk about transmission channels, sectoral, and local impacts. Thank you, Tatyana.
Thank you very much. It's great to be here. Can you see my screen okay?
Yes.
Okay, so as Glenn said, I'll be talking about transmission channels, sectoral, and local impacts. Before I dive in, I should say that I'm not going to present a comprehensive overview of all the possible transmission channels, sectoral, and local impacts, partly because we don't quite understand all of them yet. I'm also going to be focusing on just 2 types of climate change impacts, which is temperature and extreme weather events as informed by hurricanes. That's partly because my area of research is applied microeconomics, and so these are the shocks, the climate shocks, that are most conducive to studying using these methods. That doesn't mean that other aspects of climate change are less important. For example, I think economists have said very little about ocean acidification and the possible productivity effects that has. Geoffrey also brought up the disease environment, concerns about new pests spreading to areas they weren't living in before. I think these are really important considerations. Unfortunately, our tools don't work as well with these kinds of impacts. And so I'm going to focus on what I know, but I do want to put it out there that there's a lot of aspects of climate change that our tools are perhaps less well adapted to studying. And thus, this is going to be kind of a lower bound on the negative aspects of climate change that we can expect. So let me start by making the point that climate change, specifically temperature, not only affects the agricultural sector in rich countries, but the non-agricultural sector as well. So Sol gave a great introduction to our joint work from 2017, where we consider county level incomes in the United States. We further disaggregated by the type of income. And so here on the left-hand side, you see what happens to crop income at higher temperatures. So we relate annual crop income per capita in logs to the number of days that average temperatures fall into various 3-degree temperature bins. And what you see here is that as temperatures go beyond 27 degrees Celsius, crop income drops quite precipitously. So for a day where average temperatures exceed 30 degrees Celsius, you lose almost half a percentage points in crop income per capita. Luckily, such days are currently very rare, but they're increasing in frequency in the US and worldwide. But then we also consider non-farm income. And here we also see that temperatures matter. In fact, they start decreasing non-farm income at lower temperature levels than what we see for crop income. Now, the magnitudes here are smaller if you look at the y-axis, but of course, non-farm income is a much larger share of total income in the United States than is income from agriculture, and therefore, this is also very concerning. What explains the decrease in non-farm income at higher temperatures? One factor that we identify is the predominance of manufacturing. So in the paper, we show that air conditioning is protective to some extent, but a lot of manufacturing still takes place in non-air conditioned spaces. And so this last graph shows that as a county's manufacturing share increases, higher temperatures have a more negative effect on non-farm income in that county. And the higher is the temperature, the larger the decline, or in non-farm income, the larger the manufacturing share, the larger the decline at high temperatures is in non-farm income as well. So that's the first point. A piece of good news is that we also find that urban infrastructure is associated with slightly reduced climate impacts. So on this dashed line shows you the response of income to temperature for the average county in the sample, and the solid black line on the left-hand side shows the response among rural areas, which we define as having less than 50% of the population living in an urban area, because this is all at the county level. And we see that the income for these counties falls slightly more with temperature than average. By contrast, for urban counties, where more than half of the population lives in an urban area, the decline is slightly flatter. So this suggests that for whatever reason, urban infrastructure is protective against temperature shocks. And if we look at what we call ultra-urban counties, these are counties above the 90th percentile in population density, we see an even flatter response. However, even though it is statistically smaller, it's still non-trivial and negative. So urban areas are susceptible to temperature shocks as well. We take projections of temperature changes at the county level in 2080, 2100, compared to historical means, and we combine our estimates of the temperature income response to predict county level losses in net present value between 1991 and 2100 relative to no warming. Just for reference, I'll say that for the United States as a whole, using a 3% discount rate, our models indicate a median loss amount of $6.74 trillion in 2011 dollars. And we consider a range of climate models. The 10th percentile is a loss of $10.4 trillion, and the 90th percentile is a loss of 4.7 trillion US dollars. So that's for the country as a whole. When we consider the spatial heterogeneity for total income, that's on the left-hand side, we see that there are counties that lose quite a bit, and then there are counties that will actually gain. So there are two reasons that we see gains here. One is because we do stratify counties by urban versus rural, and urban acts as somewhat protective against temperature shocks. The other reason is that we allow for adaptation by allowing for a very flexible relationship between temperature and incomes. And that shows that some counties, because they're already well adapted to climate change, could actually gain from it. Now, I should say, as Sol pointed out in one of his first slides, that the temperature distributions we're going to see by the end of the 21st century are quite different from what we see in the United States today. So this does involve out of sample extrapolation, and therefore some uncertainty as to what the exact correct numbers are. And then here on the right side, we see farm income. And here we don't see any evidence except for a few counties on the West Coast that there is going to be any gains in the agricultural sector from climate change. Another aspect that I've studied in my work is the fiscal consequences of both temperature and extreme events. So in the work with Sol, we look at how transfers from the federal government respond to temperature shocks. So for example, if temperatures harm health, some transfers from the government through the healthcare system could help buffer that impact. In the case of temperature shocks, we see that the relationship is actually very flat. So this suggests that in terms of the current social safety nets, at least in the United States, the income shocks as a result of temperatures are not being buffered by transfers. When we consider crop income, we do see some evidence that there is a safety net. So we see crop indemnity payments go up through the crop insurance program in the US, and we also see an increase in crop disaster payments at high temperatures. But for the economy as a whole, total transfers do not meaningfully increase. So this is a good point to transition to the other kind of shock that I have studied, and that is extreme weather events, specifically hurricanes. So I've considered the effect on county level incomes in the United States of experiencing a hurricane shock. And there, unlike with temperatures, I actually don't find any evidence of a decrease in income following the typical hurricane. I do find some evidence of a medium run decline in the employment rate about 5 years after the shock. What the strongest response at the county level in the United States seemed to be is shown on the right graph here, where following the hurricane shock, we see transfers from the federal government increase significantly and persistently. And I should say these are not transfers that are earmarked as disaster-specific transfers. Those I examined separately. These are transfers through the standing social safety net, such as unemployment insurance and public medical benefits. So this is both good news and bad news. The good news is that it suggests that social safety nets could be important buffers when it comes to extreme weather events, and they could provide some insurance, at least at the local level, against them. The bad news is that it also means we may be underestimating the fiscal costs of extreme events quite substantially. I do some calculations to compare the magnitudes of these transfers, which are not specifically designated to be disaster related, to transfers that are formally given as a result of the event. And I show that the non-disaster transfers are actually larger in magnitude, substantially larger than those that are formally given in response to the natural disaster. Another aspect of the impact of hurricanes that I have studied is the local healthcare system. So we kind of think about the health effects of extreme events being limited to immediate mortality they cause, and perhaps by making people poorer, they could have some longer run health ramifications. However, extreme weather events such as hurricanes also disrupt the healthcare system, which could have ramifications for people who are not necessarily directly affected by the event as well. So what we do here is also look at the United States and study how healthcare utilization, and this is specifically elective healthcare utilization, evolves in the aftermath of a hurricane. On the left-hand side, we see what happens in response to the average hurricane. So in the month of landfall, elective healthcare decreases by about 7.5%. Now, the good news is that it rebounds back fairly quickly, so that 3 months after the typical hurricane, it's back to where it was before. However, this could have ramifications for the health of individuals who missed out on their elective care, whose care was delayed or potentially completely eliminated because of the hurricane. And that's something that we're currently in the process of evaluating. Another thing, as Sol mentioned, hurricanes are expected to become stronger as climate change sets in. So we also consider hurricanes that have higher wind speeds at the time of landfall, and we see much more substantial decreases on the order of 25% decline in elective healthcare in the month of the hurricane in the county where it makes landfall. We see a similarly quick rebound, but if you add up the decrease and perhaps this subsequent increase later on, not all of the elective healthcare gets made up. Now, this is not clearly a bad thing. As some of you might know, a lot of healthcare in the United States is thought to be wasteful. So whether or not this has ramifications for health is still a question that we're in the process of investigating. But I think the impact on the healthcare system itself should not be ignored as we go forward and consider these events and how these events might affect economies in the future. Finally, I want to talk about my studies of Hurricane Katrina to give some examples of how complicated it is to think about transmission channels and local impacts and make predictions with respect to any specific event. So with Laura Kawano and Steve Levitt, we looked at the incomes of individuals who were residing in New Orleans prior to Hurricane Katrina, which hit New Orleans, Louisiana in 2005. And using their tax records, we were able to follow them over time, regardless of where they moved. And we estimated how their incomes evolved in the aftermath of the hurricane compared to individuals who initially lived in unaffected cities. So perhaps unsurprisingly, given how devastating Hurricane Katrina was, we see a significant decline in incomes in the year of the hurricane and the year after. And this is in thousands of dollars. So people lost on average $2,000 in the year of the hurricane and $2,000 the year after. What is surprising is that the incomes then not only bounce back, but they actually outpace the control group. so that by the end of our sample period, and even as early as 2009, the victims of the hurricane are earning $2,000 more per year on average than they would have absent the hurricane. And this is a non-trivial increase relative to the mean earnings in the sample. Now, what explains this surprising increase? In the paper, we show that there are likely two mechanisms. First, the hurricane destroyed a lot of the housing stock in New Orleans and drove up housing prices. And this has been documented in other work as well. So it created some inflationary pressure, and as a result, the equilibrium wage in New Orleans also increased. So part of the increase in wages that we see here is nominal rather than real. But I think it also is a nice illustration of how these events can create local inflationary pressures. The other explanation for this increase is that this hurricane also pushed people out to places that on average had higher wages. So New Orleans was a struggling city economically. By forcing people to move, the hurricane helped them increase their income. Now, I should be very clear that this does not mean that welfare increased, right? We don't observe the asset losses that these individuals experience, and obviously they could have moved even before to experience this wage gains. What I think it highlights is that the ultimate impacts of an extreme event on outcomes is potentially very highly context dependent, and that, for example, Hurricane Harvey affecting Houston could have very different long-run ramifications for the affected individuals than Hurricane Katrina hitting New Orleans did, because of the type of local economy that was in place at the time. On the right-hand side, you see results from a study of the effects of Hurricane Katrina on long-run mortality of its victims. And these are elderly and long-term disabled for whom we obtained administrative records from the US health insurance for the elderly called Medicare. Now, our hypothesis was that, as I mentioned, by creating income shocks and wealth shocks, hurricanes could potentially create long-run mortality increases as well, in which case just looking at the short-run disaster toll is an underestimate if the hurricane is leading to deaths that happen years down the line. Here too, we found unexpected results. So the hurricane initially increased the mortality rate of this cohort, which is not surprising. And this increase is actually quite substantial. It's about 0.5 percentage point increase in mortality per year, which is about 10% of the mortality rate for this population, which is elderly and long-term disabled. What is surprising is that in the long run, the hurricane actually led to a mortality decrease for this population. And this isn't just because it killed off the sickest people, making the mortality rate lower a couple of years after. If we look at the total mortality risk, which is this dashed line here, by 2013, which is the end of our sample period, these individuals are about 2 percentage points more likely to be alive than absent the hurricane. And this is inclusive of the initial mortality increase. Now, in this case too, I'm not saying this is how every hurricane is going to affect every location. And this is the point, that I want to end with about the location mattering for the ultimate impacts. So we show that most of this mortality decrease can be explained by people moving to healthier places. So again, the Hurricane Katrina caused a massive dislocation of New Orleans residents. And because it was a high mortality place prior to the hurricane, on average, people moved to places where mortality was lower. And we show that movers' mortality evolved almost 1-for-1 with their destination mortality, making context very important to consider when we're thinking about the long-term impacts of any given extreme event. So again, I don't want you to think that, this is necessarily good news. The point here is that we need to think really hard about the environment in which a climate shock is happening in order to understand what some of the long run ramifications will be. And with that, I will end, and I look forward to your questions.
Thank you, Tatyana, for these insights. We will now turn to questions for the presenters. Questions from Milan. People will interject. There's also the Q&A feature. Just click on the three dots in the lower right corner to start that up. If there are any questions from the other panelists, they can unmute themselves and ask.
Glenn, can I give the floor here to some speakers here in presence?
Precisely. That's fine.
If you come here.
Hi, it's Riccardo Salluccio from Lewis. I got a question for Solomon. In the analysis, I was wondering whether you really went to, and this is about output, whether you went and eventually determining the social cost of carbon in the traditional way, because you were really close eventually in relation to that analysis. And the second one is about discount rate. I saw in the slides there was a reference to 3%, and I was wondering whether it was 3% throughout, or whether this was in relation to, you used for different regions, different discount rates. For example, in the EU, which is pretty committed in a way to do more than others, whether you use a lower discount rate.
Those are.
The mic on? Can you hear me? Okay, so this is a question that I have for Professor Hsiang. So whether in the analysis that you present, like why theoretically would we expect to see growth effects instead of level effects in GDP? Like what type of outcomes would you think would display growth effects versus level effects? And how do we go about distinguishing between these two types of effects econometrically in the analysis?
Okay, I think also Filippo has a question for Professor Hsiang.
Okay, I have a question to Tatyana. So we know that climate change generates higher temperature, but also makes temperature more volatile and makes extreme more frequent. So usually the literature discuss the effect of extremely hot temperature, but what I want to ask is that there are also evidence of effects of extreme cold temperature and in what direction, and also in general effects coming from volatility of temperature itself.
Last question from the floor, please.
Yes, so, okay. Christoph Meinerding from the Bundesbank. So I have a question to Solomon Hsiang about the estimation of this marginal product of climate, how you called it, and to what extent you take international relations into account there. So my concern is that a lot of these developments that we see in climate change happen at the same time in many countries, right? So, and if I think of Germany, for instance, of course, the temperature in Germany has an effect on the GDP in Germany. I can very well imagine that. But of course, the temperature in France may also have an effect on the GDP in Germany, just as an example. And there may be many effects like that. And I wonder how that approach that you presented can go together with international trade data or anything, and whether my concern is just a second-order concern or whether there's really something more systemic to it because the climate change is happening on a global scale in many countries at the same time.
Okay, Glenn, I think we collected a lot of questions. Over to you.
Great. Yes, no, those are great questions. Saul, why don't you go first, and then Tatyana.
So those are great questions. Thank you very much for those. I'm just going to sort of run through them. So there have been a lot of efforts to compute the social cost of carbon, which is, for those who are unfamiliar, it's a measure of what is the total global social externality that results from the marginal emission of CO2 or other greenhouse gases today or at any moment in the future. And so there have been many efforts to take the kind of econometric results that I showed you and translate them into an SCC, as we call that, the social cost of carbon. And then one idea is that you could take that measure and you could use it, for example, as a tax on carbon or something. So that's kind of what we would think of as the Pigouvian tax on carbon. When you compute the SCC, as we pointed out, a discount rate comes into play and becomes very important in determining what the overall costs look like. For the growth results I've shown you, we've actually not been computing SCCs. There have been some very good other papers that have taken our results and applied them to compute an SCC. So I would refer you to a Rickey et al. Paper by Kate Rickey at UC San Diego and her colleagues. They took the results I showed you, computed a social cost of carbon, and depending on the different types of assumptions you use, you get different numbers. They tend to be substantial. In general, it's in excess of $100. Just for interpretation, the overall implications of a social cost of carbon that is about $100, given emissions today, that suggests that sort of roughly that the externality in emissions today would be roughly like 5% of global GDP, given in destroying value in the future. But of course, that number changes if you use different discount rates. The cost from tropical cyclones that I showed on the slide, that was a cost presented in that paper, and that was kind of just an example calculation. It's actually relatively straightforward to take different schedules of costs that we project and translate them into different types of measures. So if people have different views on discount rates, you can always translate them. Glenn actually has some really interesting work on different types of discount rates that should be used, and so he might have some additional thoughts on that. Should I just run through them all, Glenn?
Yes, why don't you, and then if that's okay with Tatyana, we'll give you two separate interventions there.
So there was a very good question about growth rates versus level effects. And so to be very clear, I said the word growth rates because of how we compute what the effects are. We're looking at year-over-year changes in the log of GDP. It's very insightful to focus on the question of growth rates versus level effects. Determining whether or not the effects that we observe to occur in the data persist for very long periods of time is one of the most important research questions in this entire field. It is a very difficult question to answer, in part because we simply don't have enough data to get very, very statistically precise results about the very, very long run impact of these shocks. So theoretically, we have pretty good reason to believe that there can be very persistent effects, because if a negative event causes people to reallocate resources away from investments that make payoffs in the future. So for example, maybe I turn up the air conditioner, I spend a little bit more money on air conditioning, so I have a little bit less money left over to invest in something that's productivity enhancing, like a machine, then in future periods, I'll be paying for that in terms of foregone production. So theoretically, it's not hard to generate that kind of result. The question, though, is whether or not it happens in practice. And so in the work I showed you, in the work with Tatyana, and in other people's work, there have been a lot of efforts to try and understand whether that's happening. And the way you do it is you look at a shock today, and you look at the full trajectory of impacts as far as you can in the future, actually very much like Tatyana's slides were showing. And so if there's a period at which in the future growth rate is accelerated because of an adverse shock today, then you would see that those effects are level effects. I think what we are observing in response to COVID around the world today is very similar to that. What we tend to observe in the data is that at least central estimates do not return to the pre-event trend, which would suggest these effects are relatively persistent. However, you have to be careful, because as you go further and further into the future, the level of uncertainty about the cumulative effect tends to decline. And so those projections become increasingly uncertain, and it becomes very hard to exclude the possibility that populations are recovering. So that's, I would say, still an open question. The last point about the role of international relations and international trade, I think, is a very important point. And people are really starting to study that more and more. I think we've gotten quite good at trying to understand what are the first order or zeroth order impact of these types of shocks. And now the research community is starting to focus on the spatial relationships that occur between shocks that occur in different locations around the world, or that might be occurring in a correlated way. In some cases, populations are able to co-insure one another if they're not suffering shocks at the same time. But in some new work, people are starting to show that a lot of climate change effects look like aggregate risks because they're occurring to many people simultaneously. And so, as you could imagine, that would cause global prices to respond and will generate new types of things. So that's an area of active study.
Thank you, Sal. Tatyana.
Great. Thank you for the question. So one of the questions was about the cold temperatures. And indeed, we do find evidence in the work with Seoul that county level incomes do decrease when temperatures get colder. The relationship is not as strong as it is for hotter temperatures, but for the coldest temperatures, it is statistically significant. So that is important to keep in mind. One reason why, another reason why some counties might gain as a result of climate change is because of the decrease in the number of cold days that they face. And then in terms of the variability, I think that absolutely could have a separate impact on incomes apart from average temperature. There's a recent paper by Maximilian Kotz in Nature Climate Change exploring the day-to-day temperature variability, the role of day-to-day temperature variability in economic growth, and showing that it does reduce economic growth, holding average annual temperatures constant. So I think where it's not, what is not clear is if you sort of did the approach with fine degree bins and counted up the number of days in each bin, and then you added on top of that temperature volatility, whether temperature volatility would have a separate effect in that specification. That would be very econometrically demanding. So I think there's some evidence that temperature variability matters, but it hasn't been shown whether it matters if you sort of control for the full annual distribution of temperatures as we do in the paper.
Thank you. We are almost out of time, but I did want to come back to something that Sarah Breeden had discussed, and that was climate scenario analysis, which is a key tool for central banks and supervisors. And that really takes the next step, not just the link between future climate outcomes and the economic impact, but also the impact on financial institutions. There again, you need this granular exposures. It depends whether it's a drought or a flood or a wildfire on your asset. So it's kind of GDP versus perhaps the financial sector. Any thoughts on how your methods and processes might be extended or brought to bear on climate scenario analysis? Saul or Tatyana?
I think these type of techniques are being incorporated into scenario analyses that different groups and banks are running right now. So I think, I'm not an expert on how these scenario analyses are going to be necessarily applied internally, like for example in stress tests, but everything that is done that we analyze kind of comes through looking at specific climate change scenarios. And I think all of the methods could be directly translated. And I think different teams are doing that, also looking at the financial implications as well. One point though on the scenarios is that the scenarios that are used to analyze climate change are developed essentially without feedback from economists. And so we've actually written several articles sort of arguing that it's very important that economists become very engaged in helping us better formulate what are the scenarios. If you look at the distribution of potential projections for global climate that might occur, the biggest uncertainty is no longer physical uncertainty. The biggest uncertainty is uncertainty that emerges from policy and the economic system. So economic uncertainty is now much bigger than our understanding of the climate system, and that's a role that central bankers in particular are going to play in terms of determining which scenario is actually going to be more likely.
Thank you. Let's finish there. Our thanks to the presenters for this fascinating discussion on physical impacts and risks of climate change. I'm always struck by this coupling of uncertainty and heterogeneity in this work. Let me hand it back to Milan.
Thanks a lot, Glenn. Thanks to Solomon and Tatyana again. Clapping hands for them.